So, I mean, water is your feedstock. So there's I hope that the companies that are doing these projects in Australia have looked at the numbers and decided there's enough water. Maybe desalination is their only option. And that's not a bad thing. It's as long as you manage it and you're aware of it, you put enough energy resource in for it. Chemicals is an issue probably with desalination, because there's been issues with chemicals this year, we're getting that settled down. So I don't really see an issue with, I'm not dead set against seawater desalination in parts of the world where it's absolutely necessary. So you go to Israel, you go to Saudi, Spain. They do it on a massive scale, not just the sport industry, but public supply as well. But I think in the UK, if we end up doing seawater desalination, we've probably failed at innovating correctly in how we should be getting that water and where we should be getting it from.
I had a question for you, Colin, in terms of, why is it water reuse is particularly difficult for industrial clients by virtue of the level of contamination that it sees. And at times, especially just talking at least from a pharmaceutical perspective, you have this issue of the efficacy of pharmaceutical removal. And you may need different forms of treatment on your effluent plant, right? So as an example, ibuprofen has a removal rate of more than 90%, carbamazepine has a rate of less than 10%. So the default that companies are doing are sending it off-site for incineration. What do you do in instances like that where you need multiple types of treatment, or even as far as to say different types of effluent plants on site to cope with the vast levels of contamination?
What a lot of sites do is they mix all their wastewater flows together and then put them into one treatment plant. So the earlier you can separate them out, the better. There will be some flows that you can treat, some that you can't, or that aren't economical to treat. So the Dow case study that I talked about, some of their processes produce wastewater that's particularly salty. So in that case, it's easier to just keep desalinated seawater than it is to reuse that wastewater. Going into the sea anyway. So we just continue to put that in the sea, but we've separated at the source to do that, because as soon as people end up with the other wastewater flows, it kind of renders them useless as well.
And it's also this idea of balancing that we need to use a lot more, isn't it? So the example you gave about that higher temperature river water as an example, could you, as a suggestion, bring it into site, keep it in tanks and cool it down, as opposed to just future-proofing and becoming ready for these eventualities, as opposed to having to cool it down, and that defeats the purpose and you become more energy intensive. So it's just to point out the benefits of balancing in terms of energy improvement. So I just want to bring us back now to the East Coast cluster, and the piece of the collaboration between Equinor and SSE. So just a little bit of background on the East Coast cluster. So it's obviously uniting the Humber and Teesside, and the cluster is enabled by the Northern Endurance Partnership, so a collaboration between BP, Equinor, National Grid Ventures, Shell, and Total Energies. It's one of the two including HyNet, that have now been confirmed as Track 1 clusters. So Ian, what do you think have been the most effective approaches and projects in relation to decarbonising the Humber and the ACC?
Okay, thank you. So you mentioned a really interesting word as part of that, and I'm probably going to take a slightly different approach. So it's not really about the technology or the projects particularly. I suppose what I wanted to talk about was the collaboration. So, when you look at East Coast Cluster is actually fundamentally a collaboration between three of the industrial decarbonisation challenge projects that Will referenced earlier. So NetZero Teesside, NEP, and Zero Carbon Humber, all coming together, excuse me, to basically build a common case for that vital infrastructure, primarily around carbon capture and storage and low carbon hydrogen transportation. So the more case we can build collaboratively for that infrastructure, the more likely it is to happen. So if one of the project partners, as an example, chose to kind of promote their projects over the greater good of securing the infrastructure of the region, there's a chance that it wouldn't happen because people's drivers might not quite align. So for us, it's really been about demonstrating that collaboration on the ground. There's no real, so there are some contractual frameworks that help us do that, but fundamentally it's about getting everybody behind that common needs case of the need for carbon capture, storage and low carbon hydrogen infrastructure. Otherwise, any of these projects for this energy intensive industry decarbonisation don't go anywhere.
Any thoughts on why the success or how the success of ECC?
Yeah, I totally agree, and collaboration is absolutely key. I mean, I guess the other thing is just the scale of the need. So if you look at Humber, it's the most carbon intensive of any of the industrial clusters. It produces 30% more carbon than any of the others. So it's simply essential to put that at the forefront of our decarbonisation agenda in the UK.
And Equinor and SSE plan to either convert existing caverns or create new purpose-built ones. And we know obviously developing large-scale hydrogen storage facilities has its challenges. Could the both of you sort of just unpack that a little bit more?
Yeah, I mean, I guess the first thing is just, so these are storage, just I guess starting back a little bit for people who don't have the context. We currently have a partnership at Aldborough where we have a set of gas storage caverns and salt caverns there. And it's very clear to us that hydrogen storage is going to be absolutely essential as part of our energy future. And that's really for two reasons. One is because some of the demand side cases for hydrogen are very intermittent, and power is an obvious example of that. So the key reason that we are developing hydrogen power turbines is to be able to produce low carbon dispatchable power when the wind's not blowing and the sun's not shining. And that's, you can build all the renewables you possibly can, fill your boots, and we're big fans of that at SSE. We're looking to multiply our renewables output 5-fold by 2030. But you still need something when you don't have those renewables, and power is hydrogen for power is an important part of that. But if you're going to do that, you're obviously not running that thing all the time. You're only running it when you don't have the wind and the sun, and therefore you need to be able to store the hydrogen to then push it through the turbines at those critical times. Storage is essential. On the supply side, storage is also going to be essential because one of the great ambitions of the UK is to produce huge amounts of green hydrogen from our renewables, but obviously the flip side of that is you're only producing it, one, when you've got the renewables, and two, actually you've got too much renewables and you don't need it for our electricity grid, which we also need to double. So systemically, as sort of infrastructure of national importance, we think storage at a large scale, interseasonal storage, is going to be vital. So that's probably the first important thing to say about that. The second is that, as you say, it's not easy. These are large projects, and they take quite a long time. Ian's probably much closer to this than I am, but the development cycle for these is significant. And so one of the things that we really need to see is a business model put forward for this by government. They've said 2025 at the moment, but to be honest, and we'd be happy to tell them this, it needs to be sooner to underpin that expansion. And that way we can align the technical work that we're doing to develop these projects with the business case and reach FID in time to unlock all of these other hydrogen supply and demand projects.
Yeah, no, I completely agree, Hannah. I think maybe just to build on that a little bit in terms of the timings around particularly the business model stuff. So, BEIS have got targets around hydrogen production, particularly from electrolytic hydrogen, of 5 gigawatts by 2030. If we haven't got full sight of transport and storage business models until 2025, I haven't actually worked it out on paper, but it doesn't feel like there's anywhere near enough time to develop, construct, and commission storage caverns at the volume that would be needed to achieve 5 gigawatts of green hydrogen production. So on the flip side of the dispatchable power that Hannah talked about, really broad numbers, a wind farm might be 50 or 60% effective, i.e. the wind blows 50 or 60% of the time. you can only capture the hydrogen for, for use 50 or 60% of the time. There isn't anybody we've come across from an off-take perspective for hydrogen that's willing to only take hydrogen 50 or 60% of the time, right? You need it on a continuous flow basis. So, absolutely critical that through this consultation that BEIR's got at the moment around hydrogen transport, so business models, that certainly the message we'll be sending, and I'm sure Hannah and SC will be doing the same, is that those business models just need to come forward sooner, or we need some early action ahead of those business models that are maybe more market generic, so maybe some bespoke ones for certain projects.
And on the existing cabins, what's the potential looking like in storage? Is it real? Is it tangible? Or is there a lot that needs doing in order to utilize?
No, so I think there's a couple of things to say on that. So when you think about, let's say, repurposing the existing asset that we share with SSE at Aldborough, we've got some real challenges at the moment in the near term around energy security from a natural gas perspective. So you've got this tension between, can you even consider taking out of service a piece of critical infrastructure for natural gas supply in order to move it across to hydrogen? So the long and short is we're exploring both options, and certainly a focus on developing new storage cabins at the Aldborough site, whilst also contemplating a repurposing of some cabins, recognising that it's a transition, right? So natural gas energy security is needed and necessary over a long period of time until hydrogen is fully rolled out, and even then, if there's a healthy mix of blue hydrogen in that mix, there still needs to be some kind of natural gas storage at the same time as well.
Yeah, no, very good point. And a pivotal technology, as you've briefly mentioned, is obviously the hydrogen power plant. So at its core, it features a gas turbine that can either co-fire hydrogen with natural gas, or in the future burn 100% clean green hydrogen. But obviously transitioning from natural gas to an increased mix of hydrogen to burn 100% hydrogen does not come without challenges, and that's what I want to unpack a little bit with you today. What are some of the challenges that you're seeing? Is it going to be the issue of having to repurpose these power stations? Are we looking at brand new power stations? Do we have issues with increased NOx emissions? Stuff like that.
So we are looking at both blending into our existing power stations and building new power stations. And I think blending's got an important transitional role, not least to really support the development of the hydrogen economy around it, but it's not going to get us to net zero, and so actually it's building these new 100% fired turbines, which are, which should be the priority. In terms of the challenges, I think that's really your question, isn't it? There are plenty of technology challenges and work going on which the engineers will, beaver away at and are making progress on. You can tell I'm not an engineer, can't you? Obviously, huge respect. But actually, I don't think that is the biggest challenge. I think the biggest challenge is the infrastructure surrounding it. And ultimately, we need to get the hydrogen. So, thanks to our colleagues at Equinor for looking at large-scale blue hydrogen in the area, otherwise we'd be nowhere. And we're also working on green hydrogen projects with them and separately. So we need this hydrogen. That's probably the bit that we're kind of most progressed with because of the approach that the government has taken to supporting the supply side. We need the transport and storage infrastructure, and we've already talked about that. We need a business model for hydrogen power. So actually, the good news on hydrogen power is that building a 100% hydrogen fired turbine isn't that much more expensive than building a natural gas turbine. So it's very different from power CCS, which is also a big part of our portfolio and an important part of our energy future collectively. Because on power CCS, you've got to build this carbon capture plant, which costs about the same amount as the gas plant power station to start with. So you're doubling your capex. With hydrogen turbines, you're not. So that's the good news. And actually, because of the way the business model works and they're sort of putting in the CFD for production, the OPEX isn't too horrific either. So we're not a million miles away from where we need to be, but the cost and risk profile is a bit different, and we need to, that's something that we now need to work through with government. How are we going to bring forward these power stations? Is it through some sort of alterations of the capacity market or some other mechanism? So that all needs to be put into place as well. And then, as you very rightly say, there's the technology, and the OEMs are doing fantastic work. Some of them are really leaning on this and developing ways of switching out, ways of blending, and ways of building new 100% fired power stations. And Ian said at the beginning, collaboration is key. So we're working with them to work out how we do this, and actually to start demonstrating this and put it into practice, and get real metal in the ground, and then we can show to everybody how that works.
What's the timeline looking like, Hannah, for these fully hydrogen power stations, these new power stations? What are you thinking? Is that after the deployment of blue hydrogen, so sort of post 2030? What? No.
No, I think absolutely pre 2030. I think blending could happen in the next few years. I'm trying to think what date we've said now on our KidBee hydrogen projects together, but it's sort of the second half of the 2020s. We've together again just bought Triton Power and their plant in Saltend. They're looking at 30% blend initially and then moving to 100%. So we reckon, again, that blending we should get in this back half of this decade, and 100% certainly by 2035.
Sorry.
Sorry, I was just going to add, so it's important to kind of think about when we talked about investor confidence and all those things earlier on, as other people have mentioned. So if you think about our KidBee hydrogen power station project, it's part of a value chain. It cannot be sanctioned alone. So we've got this kind of quite complex value chain structure whereby, in order to make that work, we need Aldborough hydrogen storage to be sanctioned. We need our second blue hydrogen production unit in the Humber stage production 2 to be sanctioned, alongside KidBee hydrogen power station, as well as the hydrogen transport system, as well as access to the CO2 network. So you've kind of got this full value chain that all needs to be lined up in terms of financial investment decisions. So again, collaboration with partners right across that value chain is really important. So I think we're basically, to do all of that and line those things up, we're kind of looking around at 28, I think is the kind of current.
Okay.
And that's the beauty of the cluster process and the cluster sequencing process, is that it's been designed with exactly that in mind. You get the different pieces of the jigsaw, right, fix that first phase of design, then build out from that. And with our, moving on to CCS, I suppose, with our KidBee power carbon capture project in the Humber, we're now in that last phase of negotiations and diligence with BEIS as part of the competition there. They're doing that alongside what they're doing with the transport and storage bit of the system, and then they will then to lock all of that in and move on to fit in one go. So it's very much understanding that you've got to be whole systems about this.
Any questions from the audience for the panel? Yes, go ahead.
Otherwise, is there any strategy to try and prioritise the hydrogen towards the sectors that are maybe hardest to decarbonise or hardest to integrate carbon capture into? So you talk about putting hydrogen to a power plant. So from what I've looked into, I get a feeling that power plants are maybe easier to decarbonise using carbon capture, whereas sort of some of the industrial processes where you've got quite dirty emissions, sort of the benefit from hydrogen could be a lot greater. So is the talk of prioritising yet, or is that down the road still?
Go ahead, Ian.
Yeah, so we're working with BEIS at the moment through, and as a number of other people in the room are, with the hydrogen projects that we've selected for this phase 2 process of the 4 hydrogen projects across the 2 track 1 clusters that are currently working with government to determine it. I've not heard them talk about it specifically as a prioritised industries, but we do have to be very mindful of the industries that we are fuel switching, as an example. So at the moment, hydrogen for feedstock is not kind of supported from a business model perspective. It's very much targeted on hydrogen for fuel, and at the moment there doesn't appear to be any difference between whether that's fuel for power or fuel for an industrial heating system, as an example. So for our H6 Soltent project, as an example, we've got a range of different off-take customers, some of which are industrial, some of which are power.
I think I've just got one final question before we move on to Vertex's presentation. In that, it was an interesting one. I was doing a bid for a green hydrogen vision study for a particular combined authority. And it was a very complicated bid, typical public sector, no mention of water. And I found that hilarious. Because I think what we're seeing is you've got different parts of the UK thinking about green hydrogen ambition alongside blue hydrogen, like happening now, as opposed to blue hydrogen effectively funding green hydrogen and making it more cost effective. The drive for that again could be the war. You've got an array of reasons. So on that basis, Colin, we know that I think the rule of thumb is 12 litres of untreated water or 9 litres of treated water per kilogram of hydrogen produced. What's going on in this space? Are you actively talking to people who are wanting to make green hydrogen, and what are their thoughts on where their sources of water are going to come from? Demineralized water, obviously, yeah.
I think most of the green hydrogen projects that we've been involved in are all quite small from a water point of view. So although they seem huge from an electrolyte point of view, 20 megawatt, 40 megawatt, water volume wise, these are kind of 10, 20 cubic meters per hour. I mean, you can literally turn the tap on and get enough water. So I think the challenges for those projects because they've got lots of challenges to overcome to put those electrolyzers in place, thousands of problems to solve. And if you can just turn the tap on and solve the water issue with some off-the-shelf water treatment technology, maybe that just gets shelved. But when that 40 megawatt electrolyzer grows and becomes 1 gigawatt in the ambition of that business's future, what happens when in 2040 when they need 250, 300 meters cubed an hour, and you can't get that from the tap.
So sorry, so I guess we're looking more at sort of centralized green hydrogen production, that being an issue, and we should be closer from a geographical point of view next to the sea. Is that where we're thinking the source of water is going to come from?
I mean, I think be close to, be where you can do it the easiest. I mean, if the industrial clusters need hydrogen, produce it there, because then you don't have to worry about the transport. I mean, you mentioned there 9 litres of water for a kilogram of hydrogen. The vast majority of mass in water is oxygen. So actually moving hydrogen by mass is easier than moving water. So you can argue where the water is. But we've got a pretty good water network, and also if water gets out into the environment, it's not explosive.
Yeah.
So something to think about on centralising in clusters though is if green hydrogen production is planned to be intermittent with available renewable power, does that mean your water treatment plant is sat doing nothing for the 3 days while it's not windy? Because you then got issues with water quality, chemicals, membranes drying out, etc. So it's better if a water treatment plant runs constantly. So having a dedicated water treatment plant for a green hydrogen project might not make sense, but sharing it with, say, a blue hydrogen project where there's a consistent supply of water needed for steam production, balancing the water between those two with one treatment plant is probably a more sensible approach. So the lower effects.
Thank you so much, guys, for that. Thank you.